Hi, it's time for another math easy solution. Time to discuss modeling with differential equations. Look further into it and now look over at example 1 of the example series and basically show and go over this example, which states show that every member of the family of functions y equals 1 plus c times e to the power of t, where again c is a constant, and then all divided by 1 minus c times e to the t is a solution of the differential equation y prime equals 1/2 times y squared minus 1. So the solution, again, like I explained in my last video on general overview of differential equations, to find the solution we basically need to to show that it's a solution, we need to take the derivative of this function, plug it into the differential equation, and make sure that it matches. So we'll go over that right here. So the solution, I'll write this neater. Yeah, so the solution, will have to take a derivative of this, but as you can see, this is a division of a number divided by another number like this, and both of the functions are somewhat complex, so it's actually easier here if we just notice that we could use the quotient rule. So recall from our earlier video, recall the quotient rule. Let's write that over here. Recall quotient rule, and I have the proof of this in a video link below. So the quotient rule is just a derivative d over dx if you had two functions like f of x over g of x. This would be, let's write this, the derivative of this would equal to basically f prime of x times g of x minus f of x g prime of x, or the derivative of the g of x, like that, and then all divided by g of x squared. So that's the quotient rule. So we apply that to this function there, so we have y is equal to 1 plus c e to the t, 1 minus c e to the t, and now if we're taking the derivative y prime, so our g of x is the denominator, and then the numerator is our f of x. So the derivative of the top one, that's, well, the derivative of 0, and the derivative of 1 is 0, the derivative of c to the at is itself. That's just a constant, and then the derivative of exponential function is itself. So c e to the t, and now we have to include this g, which is 1 minus c e to the t. Now we subtract, and now we subtract the top function, 1 plus c e to the t, and then times by the derivative of this, which is, well, the derivative of 1 is again 0, the derivative of negative c e to the t, that is just negative c e t, like that. Then all divided by, divide this all by c e to the t squared. Yeah, so now what we'll do is expand the top further just to try to simplify it. So this equals to, I'll write this down further here. So this equals to c, multiply this in, c e to the t minus, then we have a c squared, and e to the t times itself, that's just e to the 2t, or e to the t squared. So like that, minus, and then we, because there's a negative here, we can make that a positive, so just make it a positive and get rid of that. So now what we'll end up having is a plus, then we have multiply the c e to the t here, c e to the t, and then c e to the t times by c e to the t, again we have the c squared e to the 2t, like that. And then all divide this by, just leave it like here, we'll c, like that. Okay, so now as you can see here, this would cancel with this, and this c to the times et adds up with this one, and so what we'll end up having is y prime of our function is 2 c e to the t, and the other ones cancel, 1 minus c e to the power of t squared. So that is our derivative of the function. So, but in order for the function y to be a solution of the differential equation, need to satisfy the differential equation, need to satisfy So we need to satisfy the given differential equation, which is y prime, again, let's just scroll up, y prime equals half times y squared minus 1. Half times y squared minus 1. So our function that we were given to show that it's a solution to this differential equation, the derivative is this right here. I'll circle this like that. So that's the derivative. So all we have to do is make sure that this 1/2 times y squared minus 1 is equal to this. So it needs to equal to that. So let's just see if we can make it equal to that. So 1/2 y squared minus 1, this equals 2. And let's just plug in our y function. Again, recall y is just 1 plus c e to the t, and then divided by 1 minus c times e to the t. So what we end up having is this equals to 1/2, and then we have a 1 plus c e to the t, like this. I'll just do it like this. Squared, or actually I'll just put the whole thing under, like that. So 1 minus c e to the t squared like that. Subtract this by 1. So let's simplify this further. It's going to be written as 1/2, and then we have 1 plus c e to the t squared, and then divided by 1 minus c e to the t squared minus this 1 right here. So what we can do right here is expand the top. We'll keep the bottom here. And the reason is because in this y prime we already have this 1 minus c e to the t squared, all squared, so we could leave that. So what we'll end up doing is expand this top numerator, and then also use this this 1 multiplied top and bottom by 1 minus c e to the t all squared, so that we have a common denominator. And then just add those up. So what we end up having is 1/2 again, this is in front. Expand this out, 1 times c, what we'll end up having is 1 times itself. So again, just expanding this square. So this is 1 squared, 1 times 1 is 1, plus here we'll end up having a 2 e to the t, and then plus, multiply this by itself, c squared e to the 2t. And again, this is just basically, we're foiling this out. Yeah, so make sure to watch my earlier video on foiling, but that's pretty elementary. You can see the video link below. So that's what we have for when we expand that out. And then what we subtract here is, well, again, we're timesing here. What I'll do, just to make it a bit more visible. So multiply the top and bottom by 1 minus c e to the t all squared, and then 1 minus c e to the t all squared. So we're not changing anything, so it's still 1. So what we'll do right here is we have now the common denominator, which is 1 minus c e to the t squared. And now what we'll do right here is expand this out. So we have this, I'll put a bracket like that, and again, 1 times 1 is 1, 1 times negative c to the et is, and then do that twice because you have to multiply c to the t by this. When we expand it, we end up having is negative 2c e to the t, and then last one, this multiplied by itself, negative c e to the t times by itself, we'll have a positive, because 2 negatives becomes a positive when we expand, c squared e to the t, 2t, like that. So that is our overall function. As you can see, we have a 1, what we're going to end up having is we're going to subtract it by 1, so this will cancel. So 2c e to the power of t minus a negative 2c to that becomes positive, so we'll end up having a 4c e to the power of t. And finally we have the c squared e to the power of 2t minus a positive c squared e to the power of 2t, which is, well, just cancels out. So what we end up having is, this is 1/2, and then what we have right here, this is, those add up, 4c e to the t, and then all divided by 1 minus c e to the t squared. So what we have there, and then this 2 cancels, we get a 2, so this all becomes y prime is equal to, the half is gone actually, so 2c e to the t divided by 1 minus c e to the t squared. And again, this is exactly what we had from the derivative of this function. So this is exactly the same, and we've shown that this is equal to this. So that is true. So this is a family of solutions, because of the c could be any value, any constant value. So again, that is our proof. Yeah, so thus for every value of c, the given function is a solution of the differential equation, because again it satisfies that equation when we plug in the derivative inside. And now this figure below shows the graphs of 7 members of the family of solutions. As you can see, it looks something like this. And yeah, if you were to have some sort of calculator to do that, I just took this from my calculus book. And these are, again, these are just graphs of the function y equals 1 plus c e to the t, 1 minus c e to the t for different values of c. And that's all that this is graphing. You could call this y1, y2, y3, and then, yeah, this is y4, y5, y6. Yeah, and actually, yeah, this line here as well is a function, that's y7. And then this orange, that's our y1, this blue is y2, and then the y3 is this one right here, which is matches with this color. So it looks something like that, and then these ones go in like that. I'm not sure what exactly the c values are, but what's interesting from this is this, again, this flat line at y7. This is actually, this equals to 1. This is if you were to plug in y equals 1, you just get a flat line. And the reason is the differential equation shows that if y is getting close to plus or minus -1, then y prime is 0, and that's because our differential equation is such that, well, again, let's just write this down. So if, or actually instead of if, as y is approaching plus or minus 1, what we end up having is y prime approaches, well, remember our equation is 1/2 y squared and then minus 1. So if this is getting close to plus or minus 1, we can move this with a plus or minus 1, which is, well, we're going to have a 1 minus, this is going to be positive 1 minus 1, which is around 0. So this is approaching 0, and that's why we have this flat line, because the derivative is the slope. And again, I'll write this down here. This is shown by the flatness of the graphs near y equals 1, and y equals -1 is actually right here, if you were to look at the negative side across it like that. So yeah, that's pretty much all for today. Hopefully you'll learn from this pretty interesting example video, and also a refresher on the quotient rule if you haven't already. Make sure to watch that video link below. Anyways, that is all for today. Hopefully you'll learn, and yeah, stay tuned for other videos. I'm going to go over more examples on differential equations and more in depth into them and its solutions and approximations. Stay tuned for that. And like always, you can download these exact notes in the link below. And thanks for watching, and stay tuned for another Math Easy solution.